All right, well, thank you, Emily, and I appreciate the opportunity to talk about herders or surface collecting agents. This is as Emily said, I lead the oil spill response research for ExxonMobil, and herders and in situ burning are something I've been working on for over 15 years now, I think. And I'm excited to talk about it because I think that this kind of combination of herders to enable in situ burning is really a step change advance for oil spill response, because it allows us to do oil spill response at high speed. I think James described some of the reasons why that's the case, and I'll give you a little bit more information about what we're doing to allow herders and in situ burning to be a tool that can respond to oil spills as quickly as possible, which, if you're familiar with oil spill response, speed is the key to oil spill response. So this is what I'm going to talk about, and I'll try to go as quickly as possible here to try to maintain time. But I want to give you a little bit of background on the primary active oil spill response options that we have for offshore operations, so you can get an understanding of the need for herders and in situ burning. And then I'm going to give you some basic information about in situ burning. I think you've heard some of it, but I'll have a couple more details. And the point of that slide is to show you, or to describe, why in situ burning of uncontained oil slicks, or oil slicks that aren't contained by a boom, can be done safely, right? We need some very kind of basic protocols to make that happen. But I'll describe how that can be done and why it can be done on that slide. And then I'll go into some details about some of the work we've done with spill collecting agents. David talked about a little bit of it, but I'll give you maybe some more details and maybe some other information. And then it's important to understand, you know, David talked about, and so did James, talked about using herders to enhance mechanical recovery. And that's great, especially for the scenarios of being kind of near shore and inshore and in protected area, or in a place where we might want to get oil out from under infrastructure or vegetation. But offshore, using herders to enhance mechanical recovery will be quite challenged, and I'll describe why. And then after that, I'll give you some information on the research we've done, and then what we're doing right now to advance the use of herders and in situ burning. And James mentioned it, but we're developing really a novel jet ski system that really, I think, advances our goal here of having a commercially available system that can be utilized for spills in general, offshore spills in general, anywhere. So first slide here, the oil spill response, the need for herders, kind of one of our basic advocacy points for oil spill response inside industry is that responders need access to all tools in the toolbox. Every spill is unique, the oil is unique, the location is unique, and so responders need the flexibility of choosing what tool they believe is going to be the most effective, right? The pictures on the left of this slide show you the three active response options that we have for offshore spills, right? And that's mechanical recovery with booms and skimmers, in situ burning, and I show the traditional way of doing it with booms, and then dispersants. And just quickly, the challenge with kind of mechanical recovery and in situ burning is the need to use booms offshore, right? And both David and James talked about the logistical needs for those, right? And so what we want to do for in situ burning with herders is get rid of the need to use any kind of containment system, right? And that really opens us up. Industry advocates for dispersants for large offshore spills because speed is the key, as I said, and dispersants allow us to fly a response option at the speed of a fixed wing airplane, right? What we've developed with herders allows in situ burning to be flown at comparable speeds. We have a system, the jet ski system I'll talk about, can be dropped from an airplane, but it travels so fast on its own that it may be faster just to send it out to a spill in a location like the Gulf of Mexico, and it might be able to get out there faster than an airplane can get out there. The only offshore operational use for in situ burning was during the Deepwater Horizon incident, and you heard before, but the reason it was deemed quite effective during Deepwater Horizon. There were over 400 burns that were done, but the reason it was effective and it was used there is because the spill kept, fresh oil kept coming up to the surface over a period of 87 days. So it allowed the equipment to be brought out and brought into place. But it is interesting to note that in situ burning has only been an operational tool one time, and that's during the Deepwater Horizon incident. It was tested during the Exxon Valdez incident, and so there was a burn during the Exxon Valdez incident, but as an operational tool through the course of the spill, it was only used during the Deepwater Horizon incident. And the reason that is, as James mentioned, for batch releases, oil slicks kind of quickly spread. They break into small pieces. They can strand on shore before you can pull out these fire resistant booms. And so the booms used for in situ burning aren't standard booms. As James mentioned, these are heavy pieces of equipment that are more logistically challenging to bring into place than standard ocean going booms for mechanical recovery. So as I said, herders enable rapid in situ burning because they require a small amount of it, and they can travel out to a spill quickly and don't have the logistical limitations of either in situ burning with booms or mechanical recovery. And it's quite obvious aircraft can travel at speeds many times, at least an order of magnitude faster than other than response options that are burdened by boats. With this slide, I just want to give some more of the background on why the basics of in situ burning, so you can understand that uncontained burns can be done safely, right? So we talked about this. Why do we need herders? Because we have to have oils thick enough to burn. We're not burning the liquids in an oil slick. We have to produce volatiles, right? And so you need the heat from the burn to actually continue to produce volatiles. So if a slick isn't thick enough, as David said, the amount of heat that is necessary to produce the volatiles is not there because you lose too much heat to the water column. The slick itself actually provides insulation. And so oil that is uncontained at sea will naturally spread much less than a millimeter very quickly. So that's why you need herders or a boom to thicken oil slicks before you can burn. So oils must have some volatiles in them. I would argue that we don't need fresh oil, right? Oil, the window of opportunity for in situ burning depends on the oil. So the oil can't have weathered so much that the volatiles are gone. And it also can't have emulsified and had too much water in it, right? The rule of thumb is 25% water or more might be too much because it takes a lot of energy to boil water. And so that heat that is needed to sustain combustion is lost if there's too much emulsification. But the window of opportunity for burning it can be significant depending on the conditions and depending on the type of oil that is spilled. But in situ burning is very efficient, right? It depends on the oil thickness. So in situ or herders can take oil that is spread less than a millimeter thick and make it maybe 3 to 5 millimeters thick, right? But the thicker the better. So if we could make an oil say 4 millimeters thick and it's going to burn down to a thickness of about 1 millimeter, right? So that would be about a 75% burn efficiency. But it turns out that when we did field tests of herders and burning, there's this chimney effect, right? Burns, I think you saw the video that David showed. Burns are quite energy intensive, right? Crude oil has a lot of energy in it. And so you get this chimney effect from the flames that can, even for a 4 or 5 millimeter thick slick, the flames can go 35, 40, 50 feet into the air. And so there is a chimney effect, right? There are convective winds that are actually coming in to feed the fire, and they're coming across the surface of the slick to actually thicken it. So what we found in field tests is that slicks that might have been herded to be 3 to 5 millimeters thick must have been 10 millimeters thick. And that slick burns down to 1 millimeter. So you can get over 90% burn efficiency with herders. And another important thing to know is that oil burns very quickly. The rule of thumb, when you have a fully engulfed slick burning, it burns at the rate of 2.5 millimeters of its thickness per minute. So if we get an oil that's 1 inch thick, it'll burn down to, and it will extinguish with over 90% burn efficiency in about 10 minutes. Now it takes time for the flames to propagate across the slick and for it to become fully engulfed. But it's a free-floating oil slick is very unlikely to burn for, if we put a pretty large safety factor, it's very unlikely to burn for more than 30 minutes. So what that means is that we can understand where the slick is relative to nearby infrastructure. And if we know the conditions of the winds and the currents, we can predict how far that slick is going to move before there's no way that it can continue to burn. So with some very simple protocols on distances from from locations that we're concerned about, and knowing the conditions of the wind and the currents when you start the burn, you can predict how far that slick is going to travel before it self-extinguishes. So David talked about this a little bit, but just a little bit more information for me on what surface collecting agents actually are and what they do. So I have these kind of very basic cartoons on the right of this slide. This is the traditional way of doing burning with booms. But as we said, herders don't require a boom. They require a surfactant boom to thicken the slicks. I tell everybody you can go to your kitchen tonight and get a cake pan, and put some tap water in it and put some vegetable oil on the cake pan, and then put a couple drops of Dawn dish soap onto the cake pan. And the surfactants in the dish soap are going to do the same thing that the surfactants in herders do. They're basically the same type of molecule, a surface active compound. So if you drop those if you drop that Dawn dish soap on the side, outside the slick onto the water surface, you will quickly see the slick thicken. You saw the video that David showed. So the idea here is to spray the surfactants carefully around the perimeter of the slick and avoid overspraying on the slick, and you'll get the slick to rapidly come into a much smaller area, and therefore it thickens. So spill collecting agents require at least an order of magnitude less product than if we were going to treat the slicks with dispersants. That's an important thing for kind of the environmental aspects of using it. There's always a challenge arguing that you're going to use a chemical response, but compared to dispersants, to treat the same amount of oil with herders or spill collecting agents, you need at least an order of magnitude less herder, and maybe even more than that, to do the in situ burning operation. Spill collecting agents were originally developed for open water. The work on spill collecting agents was done by the U.S. Naval Research Lab back in the late 60s and early 70s. In the 2000s, when we came back to using herders and we were considering using them for in situ burning, most of that research was focused on using herders and burning in ice. And so it's got this kind of idea in people's minds that herders are an ice or a cold regions response option. But if you go back and look at the research that was done since the 2000s, and the research that was done back in the 60s and 70s, most of the testing was done on open, ice-free, temperate conditions, right? And so we talked about, well, I'll describe on another slide. But so the goal here is to develop another tool that can be rapidly applied, right? As we talked about. On all these slides, I'm assuming that these are going to be handed out, but I tried to cover anything that requires a reference, and I have all these references on here. So I'm going to go very high level on these things, but if anybody wants to get some more information on herders and the background and what's been done to develop herders to this point, I have a whole list of references on each one of these slides. So I mentioned this in the last slide, but we need to carefully apply these surfactants around the perimeter of oil slick, and very quickly, it happens in a matter of minutes, the slicks will contract into a smaller area and make the oil thick enough to burn. We have 2 surfactants that are available on the EPA's national priority list for use in waters of the United States, right? So they are accepted on that list, so they could be used, assuming they get approval during a spill, as James described. One of them is quite biodegradable and very low in toxicity, which is the one we'd kind of recommend for general use. So with this slide, let me just describe quickly why the challenges we have with surface collecting agents and mechanical recovery. So the research in the 60s and 70s focused on using herders to enhance skimming, and there's been research done since then to enhance skimming, but herders do not eliminate the logistical issues that are inherent in using mechanical recovery. First, you need this kind of system here, boat and booms, to do the operation to begin with offshore. But then you need the additional equipment, the logistical challenges of collecting the skimmed oil and water mixture, transferring it to another vessel to take it to shore, so skimming operations can continue. So those logistical challenges are significantly eliminated by the use of herders to enable in situ burning. But the other challenge is that skimming herded but free-floating oil slicks is just inherently inefficient. And what they found in the 60s and 70s, and James mentioned that CGA had herders and a capability to use herders in the 80s, but that was for the idea of using them for mechanical recovery, but they never were used, right, offshore at least. And that's because for mechanical recovery with a boom, the herder, or the skimmer will be placed at the apex of the boom, kind of the sweet spot. And then it's always in the same relative location, right, to the boat. So there's no challenge with kind of the skimmer not being in the right spot. But with free-floating oil slicks, what they found in the 70s is that the skimmers had to be continuously repositioned in the oil slicks, which made it much more inefficient. But also, skimmers were developed for thick oil. In fact, the ASTM test to evaluate skimmers requires that the oil in the test system that you use be multi-centimeters thick. And oil in a boom that's completely full will be many inches thick. In fact, a boom will fill until you start losing entrainment of the oil underneath the skirt of the boom. And an ocean-going boom system will have a skirt that is maybe 3 feet deep, right? So the oil at the base of a boom can be even a couple of feet deep, if not more. And then you put the skimmer at that location, it is in kind of the ideal spot for skimming as efficiently as possible. So I say that the challenge is for mechanical recovery offshore, but James described this and David described this, but surface collecting agents can be effective in a quieter environment in marinas or in enclosed areas, and they can be used to remove oil and sheens from under structures, and then you can get them out into free and open water and allow other types of operations to recover the oil, and you also have more time because there's less energy in the system. So there's been over 15 years of research to prove surface collecting agents enhances in situ burning. I mentioned how most of that work is done under temperate open water conditions. So again, this is not an Arctic or an ice only tool. It is an open water and temperate conditions, and even equatorial tropical conditions. Surface collecting agents have been formulated to be low toxicity. The one that is made with hydrocarbon-based surfactant is called Thick Slick 6535. That's available for sale by DESME. We've done tests on it. When it was listed with the EPA, we had to do the standard toxicity tests. These concentrations, which caused a response to the organisms that were tested, is an order of magnitude. It means it's an order of magnitude less toxic than most of the dispersants that are available for use today, including Corex at 9500. And based on the EPA, based on these toxicity thresholds, these are considered practically non-toxic as defined by the EPA toxicity test. That same herder or spill collecting agent has undergone biodegradation tests, and it is quite biodegradable. In fact, it is in 20 days, it's over 99% biodegraded, so it's quite biodegradable as well. But I don't mention the other herding agent that was listed. It's a silicone-based surfactant. It's called OP40. It is significantly more toxic and less biodegradable, but it is a better herder. So as David said, there may be situations where it works better than the thick slick herder, but I would say that the rule should be use thick slick as the herding agent, unless it's certain that it's not going to work. James mentioned this, but herders have been have this thinking, the conventional wisdom, that they have to work in very calm sea states, right, or low energy sea states. But Garrett and Berger went out offshore, and they actually went to the mouth of the Chesapeake Bay in 1972, if you can believe that, and spilled some heavy fuel oil. And they kept it herded for 2.5 hours in 6-foot seas with numerous whitecaps. So there's reasons why herders actually knocked down whitecaps and allowed that to happen. 2.5 hours is far more time than we need for in situ burning. So herders may have a window of opportunity for in situ burning that are actually far greater than burning in conventional or in fire booms today. So this is another picture or another graph or another video. This is similar to the video that David showed, and actually in the same location in New Hampshire at the Krell Army Research Lab. This is Ian Bust, which is a colleague of David. He's the first person to kind of suggest that we use herders for in situ burning. This is a real-time image or video, is the reason I'm showing you this, and it shows you how quickly you can actually see the oil moving across the water surface. It takes Ian about 30 seconds or less to walk around the perimeter of this slick. In his hand is a small little syringe where he's dropping the herder, right? So that's why it just takes a very small amount of this, because eventually the herder can form just a monomolecular layer on the surface of the water to do its job. And we can describe this if you have any questions, but you don't need a wall to push against. The herders work just as well in the middle of the Pacific Ocean without walls as they would, because it is a surface effect as it would in a system like this. David mentioned some of the tests we've done, but one of the first tests that was done with herders and in situ burning was a field test done during a joint industry effort in the Arctic, and oil was spilled off of this very large ice floe. There's actually a couple of people dropping oil. This is folks from SL Ross dropping oil. They're standing on this ice floe dropping oil into the water. 630 liters of this Norwegian crude oil was put there. A vessel went around and delivered the herder with a garden type insecticide sprayer, and then the same boat came in and dropped an ignition source on the upwind side of that slick, and the burn was quite effective. And this is one of the first tests where we saw that this chimney effect happened. This slick was expected, based on lab tests, to burn with about 75% burn efficiency because it was expected to be 3 to 5 millimeters thick. But in fact, they collected the residual oil after the test and measured it and found that they got over 90% burn efficiency. That's where we got the idea that this chimney effect was important in large field spills. I won't show that video. We've done additional testing to develop a delivery system. There was a test done in 2015 in Fairbanks, Alexa, to develop this helicopter-based delivery system that uses a helitorch to ignite things. There were some fundamental flaws with that caused us to move on. This is the field test that David talked about, and the only thing I'll mention quickly on this is something that was very interesting, that's kind of eye-opening when we did this field test. When you look at this picture here in the upper right, the slick is kind of quite obvious, right? Black slick and then clear blue water, right? These little man overboard boats, and David Cooper was actually on one of them, spraying the herder for us. And you can see how they split through the slick. Well, it turns out the guys on the boat had a big challenge actually telling the slick from the water, and they were driving the boat through the middle of the slick and actually breaking it in two, which is a problem, right? Because if you ignite this part of the slick, the flames can't propagate across a gap. And it's because they didn't have eyes in the sky. The eyes, like there was this plane, you can see its shadow here, and we had unmanned aerial vehicles flying over, and it was obvious to us on the boat because we had the video images from those systems, and it was hard for us to originally understand why they kept driving through the slick, because we're like, how come you can't see it? But they couldn't see it. And what the lesson learned there is what you really need, the captain of a boat like this actually needs to have the video feed, because it would be very easy for him with the video feed from some sort of aerial observing system, and an unmanned aerial vehicle is ideal, or a small drone. He would have been able to very carefully treat all of this with herder and do a better job than was done during those tests. So James mentioned this, the research has evolved to develop a delivery system, and we've taken an off-the-shelf jet ski. It's the one we're using is called a Sea-Doo Spark. It's quite an inexpensive thing, between $5,000 and $10,000. We cut the top sides off of this system, and then we've developed our own top sides, and it's outfitted with cameras, it's outfitted with tanks to hold herder, and it's outfitted with tanks to be basically a flamethrower to ignite the herded slick. So this system here is kind of a one-stop shop, and it has a virtual reality camera on it, so the operator of the system can be located pretty much anywhere. The vendor we're using is called Tactical Electronics, and they're calling the system the Nomad because it can go out and operate kind of on its own. It has a tethered unmanned aerial vehicle to get the eye in the sky view for the operator can use. And so this system is operated like a virtual reality system. The operator will put on virtual reality goggles and operate as if he's sitting on the back of it, and have the view from the air to see where the oil slick is relative to the water, so we can carefully go around and spray herder. And then the system will come back, because it has, as I said, a flamethrower that sends out gelled gasoline to ignite the herded slick. I won't go through all these details, but this system is also a very capable remote detection system with this tethered UAV and other systems. It has VOC detectors. It has a collision avoidance system to allow it to be safe when we go offshore, and it can travel very quickly, 65 miles an hour. It has a very large range even off the shelf, so it can have significant operating times. And because it can go so fast, by the time you could get an airplane up in the air, this system could be out to oil spills that are, unless they're like over 100 miles from shore. But this remotely manned surface vehicle, or the jet ski, is deployable from a ship. Our vision is that every significantly sized offshore vessel has one of these on it, not just for the ability to do herding and burning, but for it to be its advanced scout system to identify where slicks are. We can drop it from a helicopter, or we could drop it from a plane that has a large enough door to allow the deliveries, the jet ski to be thrown out the door. And we've done some testing. The system exists, the prototype exists. Hopefully this video is coming through, but that's the system on some of the first tests that we did to show that the remote control system was working. You'll see this thing kind of nose down really quickly there. It has an ability to reverse the thrusters to act like brakes, which is kind of interesting. We've done other tests. There were some field tests done in Kazakhstan in 2018. I mentioned those because it was done by a group that didn't have any experience with herders, and they had a very successful test, right? I just sent them kind of very basic instructions on how to do those tests, and I wasn't there, and no other real expert on in situ burning with herders was there, and they did a successful test. I'll mention the Chevron drill last May. They request endorsement of surface collecting agents for in situ burning, but RRT6 didn't give the endorsement. And the reason they didn't is they had concern about burning of free-floating oil slicks, right? And so that's the reason I described that we can burn free-floating oil slicks safely, because we know that free-floating oil slicks can't burn for very long. There was also concern in that drill when we went to the RRT6 that that herders were a tool for cold ice environments, and as I mentioned earlier, they have been tested in temperate regions far more than they've been tested in ice environments. Our future plans is to go, there's a plan to do a field demonstration in Canada next year, and we hope to take our jet ski up to Canada and do herding and burning up there. So with that, I think you could read through this, and I'll try to not spend any more time talking and give it back to the room. Thank you.
Thank you very much. I am going to now switch to the next speaker while Emily in the room unmutes and starts her introduction. Okay, there we go.
Did you want me to mute the mic?
So Emily's going to begin her introduction. We can barely hear you.
Okay. All right, let's see if this works. All right.
There you go.
Okay, so our next guest speaker is Dr. Srijan Agarwal from the University of Alaska, Fairbanks. Srijan is an environmental engineer by training and a faculty member in the Department of Civil and Environmental Engineering at University of Alaska, Fairbanks. There he is. His research includes fate and transport of oil spill and response chemicals, as well as drinking water treatment and distribution and urban air quality. He's also a National Academies of Science, Engineering, and Medicine's Early Career Research Fellow for his work on oil spills. And a fun fact about him is that he's lived in some of the hottest and coldest places in the world, building a resilience to survive in 170-degree temperature range. He spent the early years of his life in New Delhi, India, where the summer temperatures range between 100 to 120 Fahrenheit. And so kind of like Louisiana. And in the last 13 years, he's lived in Minnesota and Alaska, where the temperatures hover -30 to -50 Fahrenheit for a significant portion of the year. So Sri John is joining us from Alaska.
Thank you, Emily, for the introduction. Just want to check if I'm audible, Tara.
Yes, you are. I hear you very clearly.
Thank you. So yeah, I'm gonna talk about some experiments we've done with herders and oil spills in Alaska, and it follows up on the previous speakers, Tim and David, and yes. So let's see, trying to advance the slide here. So use of herders in Arctic waters. So as Tim said, herders are not just an Arctic thing. They are applicable, you know, in temperate climates, in temperate weather. But what I'm presenting here is primarily related to Arctic application. So Arctic and Alaska have their own unique characteristics that make in situ burning favorable. And oil spill response in the Arctic would have significant logistical challenges and technical challenges, which makes in situ burning more interactive. And as we have heard numerous times this afternoon, that we need to thicken the oil slick, to allow in situ burning. And here is a schematic which sort of shows how the sequence of using herders and in situ burning. We have an oil spill in the presence of ice, and then you apply herders by a helicopter or a UAV, and then the slick is contracted, and then the contracted slick is ignited from the helicopter, and then you get a lot of times greater than 90% removal of oil using in situ burning. So scenarios for herder use. Herders are, as you see, there are like some different options of oil spill response here, and this sort of figure is showing like different ice coverage and different wind conditions. So you can see in situ burning is favorable when it's part ice condition, less than 10% ice, or when it's like greater than 70% ice. In case the spill is sort of self-herded by the ice. And when it gets very windy, the oil gets emulsified and weathered, and as mentioned before, it's hard to conduct efficient in situ burning for a weathered or emulsified oil. So yeah, and so this is again the aerial application of herders, crude oil released using the spill release frame. This was how we did some of the experiments and that Tim alluded to briefly, the experiments in 2015 in Fairbanks, Alaska. The oil spreads toward the equilibrium, and after the oil was spread, the herding agents were aerially applied in that case through helicopters and applied around the oil spill. And then the oil slick thickens under the herder action, and the helicopter landed on the side and loaded the heli torch, which Tim mentioned had some issues, and unloads the herder applicator. And the thickened oil slick was aerially ignited by discharging the gel fuel on the oil, and the in situ burning of oil was initiated. Now, along with those field experiments in 2015, we conducted certain other experiments which sort of exploring the effect of scale. We want to, like I think David mentioned earlier, some smaller pan tests, and so we were sort of wondering how does those tests done in the lab sort of compare with the larger field scale tests, and so we did like 3 experimental scales: a bench scale, doing basically just pans, and then mesoscale, which is here, that was done near a fire training facility at the University of Alaska, and then of course the field scale that was also done at the University of Alaska Fairbanks facility. And for all these experiments, we considered we used fresh ANS crude oil that is unweathered, and the herder used, actually there, as Tim mentioned, there are like 2 herders that are on the National Contingency, EPA's National Contingency Plan, the Celtec OP40, it's a silicone-based herder, and the thick slick then both were used in those experiments. However, the results I'm presenting here and the bend scale and the meso were done using OP40. And we simulated a partial ice cover in fresh water, and ambient temperatures were below freezing. And a lot of, if you're interested in reading more about this, I have a reference list at the end. So bend scale tests were done using, we developed this sort of a chamber, we call it a in situ burning testing chamber at the university, and which could also collect emissions and so forth and test for those. But then there were like simple pens which we often took outdoors and just in the cold environment, and had some ice blocks in there to simulate the 10% ice cover. And this is the mesoscale test. And this is the panoramic view of the field scale. It was a 90 by 90 meter, and we had some artificial ice in there that we developed there. And the impact of herder application, and you've seen a few videos which shows that you need a very little herder. So here is the bend scale. You can see the dark oil here. And then after the application of herder, the oil is like thickened. And here it's dark color is the oil, and then it's not very clearly visible on this image, but then it's a herded oil that is collected. And then this is the field scale, and these images I believe were taken by unmanned aerial vehicle, and then these are our artificial ice flows in there, and this is the herded slip. And then the ignition after the herding was conducted through a Healy torch in the case of field scale experiments, and then in the mesoscale it was done manually. Now burn efficiency, and it's a little bit has been mentioned about burn efficiency. Mathematically speaking, burn efficiency would be the percentage of oil lost. So that's mass of oil that was released, and subtract the residue of the mass of the residue, and over the mass of oil released. And burn efficiency is an indicator of amount of oil removed after the in-situ burning. And we noticed in our test that burn efficiency increased with increasing scale of the experiment, which was pretty interesting. And that alluded to that indicated that there was this stack or chimney effect that Tim mentioned was going on, was at work. A larger burn produces more energy, which creates stronger convective currents aided by rising mass of the hot air when the burn, within the burn. So sort of it self-feeds. Once there's a huge burn, it sort of starts self-hurting itself and increases the thickness of the slick. The convective currents cause the natural contraction, internal hurting, leading to a higher burn efficiency for larger burns. And letting the burn continue till completion helps achieve higher burn efficiencies. So for some of for example, the meso burns, we had to suspend because the fire here was getting, so the fire officials at the scene, they thought that it's better to extinguish it before natural extinction. So, but in the open waters, where the burn can be continued till completion, obviously will help achieve higher burn efficiency. And breaking of slick into multiple sub-slicks would lower the burn efficiency. And weathering of spilled oil can reduce burn efficiency. As I mentioned, the water mixing would need more energy to boil off the water. A higher fraction of lightweight volatile compounds in oil and lower water content in the oil both tend to increase the burn efficiency. And the percentage of ice cover can both increase and decrease the burn efficiency dependent on the slick thickness achieved and water content. Okay, next thing about herder application rates. So in the literature, the recommended herder application rates are very low. As was mentioned, it's about an order of magnitude lower than what are needed for dispersant applications. And since, and this is because the herder forms a monomolecular layer on the surface of water and reduces the surface tension. and that's how the herders work. And I'll show something about this surface tension upon the application of herder later on. But since it is applied at the perimeter of the slick, the application rates are per kilometer. So this is 5 to 15 liters per kilometer of the perimeter, or 50 to 150 milligram per meter square of the area of the slick. Now, in our the 3 experiments, the bend scale, the mesoscale, and the field scale, we measured sort of the herder application rate, and it was pretty much in the ballpark. But some experiments in the bend scale, we over applied the herder much higher quantities to just see that how the herding is affected by over application of herders, operationally speaking. And we found that it's easier to control the herder application rates in bench and meso tests, and precisely targeting herder application is challenging when done aerially. And so I think what Tim was mentioning about the remotely manned surface vehicle or the jet ski would be a very useful tool to make that application in a field scenario very precise. Now, bend scale experiments that we did over application of herder, they revealed that it was difficult to ignite and sustain the burn when the excess herder was applied. So we did 3 experiments. We didn't do a lot of them, but then with that preliminary understanding from those experiments is that, you don't want to apply too much of that thing. It won't really help. Now, management of burn residues. So these are the burn residues that we saw in the bend scale, in the mesoscale, and the field scale. And in general, the residue of unweathered ANS crude oil floated and could be recovered. As for our experiments, notice that. Now, a previous study by Shigenaka in 2014, they reported highly weathered and emulsified oil from the Deepwater Horizon spill that generally sank. So it depends on the oil and the conditions and the herder about the residue. Now, residue management decisions must be made on a case-by-case basis, considering the net environmental benefit. So as a part of the Deepwater Horizon response, it was determined by the U.S. Coast Guard that resources were needed elsewhere, and comparatively considering the residual risk from burn residue was not higher compared to taking care of other burns. Thus, the residue was left to settle into the water column and to the seafloor. So this is some of the herder monitoring on the field study that was conducted, and after the field study lasted for about 5 days, for a week. And as you see, this plot here is about the surface tension of the water in the field basin, and there was like 1 test conducted each day. So the surface tension dropped dramatically because of the application of herders. And then we monitored the water for a couple of months, and we noticed that the surface tension sort of came back to the pre-test levels. And so, and on the other side, we also mentioned this plot here is showing the OP40 concentration, the herder concentration we measured using GCMS, and we noticed that the herder concentration also dropped and this is the detection limit, dropped pretty significantly over as the time passed. Now, there are a lot of factors going on here. I'm not going too much into detail. So not sure if it was photodegradation, biodegradation, what exactly was going on. And there are people who are working on that, and there's some reports out there on that, but this is sort of what we noticed from our measurements in the field study. Now, this plot here shows the burn efficiency from other studies. So we recently did a review paper which pulled data from a lot of in situ burn studies done all over the place. And so this one is showing the different oils that have been used for in situ burning and the burn efficiency that has been noticed or reported by all the different studies. And these include field studies, these include bend scale studies and whatnot. But you see the burn efficiency for majority are greater than 80%. And again, details for all these are present in this publication. in the same publication, we also pooled data and made this plot of that uses that the thickness achieved by using herders, by different herders. So these on the x-axis are 4 different herders, and the first one is the U.S. Navy, which is now known as a thick slick herder, the OP40, the Perexit OC5, and EC9580, and you see OP40 is a little bit better than the thick slick, operationally speaking, but then all of them are, as you see, they'll take you on an average between 3 to 4 millimeters, which is a good thickness to initiate in situ burning. These are all the references that I've used in this talk. And last but not least, I'd like to acknowledge all the people involved in this research, the Joint Industry Program led by Joe Mullen, and Tim Nedwed is a part of that as well. University of Alaska Fairbanks, we got a some funding from State of Alaska Hydrocarbon Optimization Grant. And then in this field test, personnel from SL Ross, Ian Buist, Steve Potter, David Cooper were involved, and Alaska Clean Seas. We had UF Fire Department on site, and then all the personnel from the UF team are pictured here. Especially kudos to Jessica Garin and Robin Bullock as a PhD student working on this for their efforts. With that, I'll switch it over to the next speaker. Thank you.
Thank you very much. I'm going to move up to the next speaker.
Final guest speaker, George John, who's calling in from the City University of New York. George is a professor of chemistry and biochemistry at City University of New York, and his research is highly interdisciplinary, focused on the molecular design of synthetic lipids, membrane mimics, soft matter, trans fat alternatives, and organic materials chemistry. He holds several patents on innovation related to the value-added chemicals, surfactants from renewable resources, and their potential utility in food and biomaterials. So he's going to be talking about possible future directions in terms of research. Also, who has the clipboard? It's back there.
Dr. John, can you turn your video on? We can, are you sharing your Zoom?
I was.
So you've got your screen shared, so why don't you put your presentation, the PowerPoint up? And then if you can turn your video on too.
Okay, video is on.
There we go.
Hello. And share.
So yeah, your presentation. We can see the Zoom connect, but we want to see your presentation.
I was trying to share it to desktop. Can you see it?
No, we just see your okay, yeah, so that it's like your browser. So we want your PowerPoint.
Desktop. Still the same thing?
Okay, so open up your, maybe you shared the wrong screen. So open up the, where, do you have the PowerPoint open that you sent me?
Yeah, it's open right now.
Okay, so I think you probably shared the wrong screen. There you go.
Oh, I see.
Yes, perfect.
Okay,
Perfect.
sorry for waiting. Okay, thank you, Emily, and sorry for a couple of minutes, and thank you very much for the invitation to speak about this one. I'm supposed to be there, but unfortunately I'm still in New York, and I'm happy to talk about today's subject, the eco-friendly chemical herders. And we heard about a lot about herders, but I will talk a little more about fundamental science, and this is from City College, and this is a collaborative work between chemistry and chemical engineering. And first of all, I start with the acknowledgement for the Gulf of Mexico and for NSF for funding. And the fundamental question is why the oil is spreading on water. And I'm sure all of you know that one. It is much more of a surface tension, because the surface tension of water is higher than the total sum of the surface tension of the oil-water interface, and therefore the oil is spreading on water. And right now, because of that spreading of water, it creates oil spill. And these are the typical standard procedures for mitigating oil spills. One is burning or in situ burning, and dispersants, booming. These are the typical traditional ones, and there are a couple of them, skimming and bioremediation. And I will talk about mostly about how we can generate new generation herding agents as well as skimming or gelation technology, starting from small molecules which are surfactants, which are derived from biomass or eco-friendly oil collecting agents. The first project I will briefly talk about phase selective gelation technology. In this case, how we develop these molecules or surfactants to solidify oil in presence of water. We start with byproducts and co-products or waste materials which are derived from plants and crops, and we try to do some very simple chemistry. It may be a one-step chemistry, or we do biocatalysis, much more eco-friendly. We are creating molecules, and those molecules are all of with a head group. It is typically hydrophilic or water-loving. Then we have tails attached to those hydrophilic particles, and these are our hydrocarbons, relatively small hydrocarbons, maybe 5 to 16 or 18 carbon atoms. And this is coming from vegetable oil. We are connecting them by this simple chemistry, creating simple molecules. And these are our building blocks. And these molecules, when we keep it in water, in order to minimize the energy, the surfactant molecules self-organize to create different kinds of structures and functions. And depending on the structure of this molecule will self-organize to create fluid structures like micelles and liposomes or vesicles. Sometimes we are getting jelly structures, sometimes we are getting liquid crystals, and sometimes some of these molecules have the capability to herd the oil. And I will talk about those little things. As I mentioned, all these molecules having a head, which is water-loving, and there are tail, they are oil-loving. And we call them amphiphiles, or in the shape of a tadpole, and with a head and a tail. It is typically a soap kind molecule. Once we have the soap molecules, if you put it in water, we are getting micelles and vesicles, and sometimes they happen to be a bilayer. And here you can see a simple bilayer. It is just a bilayer. It is typically in our body. It is bilayer membranes are there. And if it is happening in the oil base, we'll get a reverse bilayer. And depending on the structure of the surfactants we are using, sometimes we get three-dimensional network, just like a sponge. A piece of sponge which is created by fibrous networks, and these fibrous networks, sponge can congeal the solvents, and we are creating jellies. And we have the capability to make or design molecules which can potentially useful for making water-based gels, just like the gelatin jelly, the dessert what we eat, or we can create oil-based gels, and we are using this technology for oil thickening. And where from we are deriving all these molecules, you can see these are all simple sugars, and this sugar is, again, this thickelose is typically used for baking of a cake, and sorbitol, mannitol, and xylitol, these are simple sugars And the cheapest sugars, they are typically found in chewing gums. They are edible, and we are using those kind of sugars to create simple amphiphilic structures. This is the head part, this is the tail part. It is mostly coming from vegetable oil. We are creating molecules with a head and a tail, or in other words, it is surfactants. And these surfactants have the capability to solidify oil in presence of water. Usually, if you in a laboratory or at home, if you have a oil-water mixer, if you are adding soap into that one, it is typically creating kind of a white, milky product. In our case, this particular family of molecules have the capability to solidify oil in presence of water. That's why we call them phase selective. It can selectively migrate to one phase, oil phase. It can solidify. If it is happening, this is our dream. If there is an oil spill, we can spray our simple molecules in simple, typically in alcohol or some those kind of solvents, which can solidify. We can skim it off. And we potentially did it in the laboratory. Right now it is available in YouTube, but here I am not showing that YouTube, but it is available. This is just an example. You can see this is a water diesel mixer. At that time we didn't have crude oil. Right now we have. And we can even solidify almost 30-40 milliliters of diesel in presence of water. And you can invert this vessel without a core because the diesel is gelled and it is solid enough to keep the water there, about 30 milliliters of water. And that's why we call them, this phase selective gelation. And this phase selective gelation is happened because the simple surfactant molecules self-organize, they self-assemble together to create a solid structure with this small fibrous structure under the microscope. You can see this one. And this, in this particular case, you can see this is crude oil from Gulf of Mexico. This is a crude oil. It is black is the crude oil. Initially, it is liquid. We are adding our molecules in presence of this water, and this crude oil is selectively solidifying, and we can separate them. And these molecules are safe. It's coming from sugars and fatty acids. Now I am switched gear. I'm talking about some of the interesting new cont'd molecules we developed in our laboratory. And I am sure that all of you are experts more than me. Cont'd is historically pulling together animals using a tool. Now we are trying to utilize a chemical to pull together oil, and it's the definition for chemical cont'd is oil collecting agents. And in our case, all these oil collecting agents are having a hydrophilic and a hydrophobic tail, and we are trying to utilize this molecule to reduce the surface tension of water around the oil. And suppose if you have an oil spill, especially if it is thin oil spill, whether it is Arctic Ocean or it is warm ocean, and if you can apply a herder, this is the first example I showed you. This is an ocean, oil spill, oil is spreading because of the high surface tension of the water across the periphery, and here in the right side and left side, if you are applying the herder, the simple surfactant molecules, which can reduce the surface tension of water from 70 to 9 millinewton per meter, you are somewhere around 13 millinewton, then this oil cannot move into forward direction. It has to retract it. And when it is retracting, it is fattening the oil. And this is a pictorial representation. Oil spill is there. We are applying these cont'd molecules in a solution, and it is reducing the surface tension. Oil cannot move forward. It has to come back and retract. Again, it's a schematic representation. Oil spill, applying the surfactants, and it is reduced, thickening the oil. Right now, we are applying the fire, but we never do the firing in the laboratory. This is mostly fundamental science, trying to understand the science and chemistry to develop a much more biodegradable and safer. And right now you can see here it is much more pictorial representation. This is the surface tension of the sea, water, and air. This is the surface tension of the water, oil. This is the surface tension created by oil and air. And then this surface tension, total surface tension is less than 0, then the oil cannot move forward. And these are the, you may never saw the chemistry of the OP40 and thick slick. This is the OP40. This is maybe the most, earliest version, but most efficient one. But unfortunately, they happen to be silicon-based polymers. They never may be going to degrade in the water. But the thick slick is much more of a kind of a sugar-based system. And we are developing something even interesting stuff. And the reason is starting from David, James, Tim, and everybody talk about the importance of this chemical carbon is speed, low application rate, and ease of use. And therefore, and the chemistry is, or the science is here, again, the surface tension of water should be less than 0, the total surface tension of the oil and water. And must be environmentally benign, that would be wonderful. And we are trying to develop a herding molecule. In this case, the left part, the tail part, is coming from phytol. Phytol is a byproduct of chlorophyll, and chlorophyll is in the ocean biota already. And then they degrade, they make this phytol. We try to utilize the same phytol molecules, connect with a hydrophilic part. Now it is a surfactant. And this surfactant, especially, this is coming from imidazole. Imidazole you could find even some of the drugs. And imidazole, this, we believe it is non-toxic. We did only very preliminary tests. Interestingly, this molecules has the capability to reduce the surface tension of water to 70 to somewhere around 28 to 30s. And this can herd the oil. Now we are not doing the experiment in the ocean, but we are trying to mimic the ocean in the laboratory, utilizing artificial salt water. Now we are creating a thin oil slick here in the artificial sea, and this is Gulf of Mexico oil, crude oil. And right now we are getting a thin slick. We are just applying a millimolar solution, a 1 or 2 drops of millimolar solution in this side and this corner, only 2 drops. We are applying very dilute solution of the molecule. What we synthesize in the laboratory, you can see what is exactly going to happen. Just accelerate a little bit. Yeah, now you can see how fast this is happening. And this is exactly what Tim was mentioning about that. If you have oil and water, vegetable oil or any kind of oil in a dish, if you are applying soap, it will retract. But here also it is retracting, but we keep this one for hours. It will never come back. If it is a regular soap, it will come back because the soap will start dissolving the oil and surface tension will come back to the normal. And now we are developing couple other systems. And this is mostly, we believe, could be potentially usable for warm ocean. And because there is waves are there, and here this is wavy ocean. And in this case, because the herding monolayers tend to disintegrate in sea with waves, can binding the monolayer to polysaccharides in the sea surface microlayer improve the stability and increase the dilatation viscosity? Because we need a stable monolayer in presence of a surface wave action. If it is a calm ocean, it is much more easier. And therefore, we are interested to understand what exactly, how we can create a biodegradable, interesting molecule here. And again, we are talking about, and I will, especially this one, if we can utilize the ocean biota, the micro layer of the ocean, and which contains several molecules which are coming from plant chloroplast, because there is all kind of algae is there, green algae is there, the chlorophyll is there, and all these green ocean, they may contain all these kind of similar kind of molecules, and I will show you in the picture here. This is a pictorial one because there are polysaccharides, maybe from seaweeds, and it's mostly carrageenan, and there are some other molecules, and different kind of molecules are in the ocean microlayer or sea surface microlayer. And we can utilize the chemistry of this sea surface microlayer to dampen this or minimize the wave action by engineering molecules and designing molecules which are already in the systems in the chloroplast. One example is this, again, phytanic acid. Phytanic acid is a degradation product of chlorophyll, and chlorophyll contains phytanic acid. Palmitic acid is an example, and we are trying to understand how this kind of mixture of this ocean surface microlayer can be keep the bubbles, and there is kind of a viscosity of that bubbles. This is a typical example. We are utilizing two tools, especially Langmuir project. I am not going to talk anything about that one. That is one of the tools we use in the laboratory. Another one is we are using pendant drop experiment to understand the viscosity and the ability to keep the waves. And this is exactly what is happening in chemistry-wise, because this ocean microlayer contains seaweeds. There are several kinds of seaweed. This is one example of the red seaweed, which containing lambda carrageenan. This is having galactose kind of sugars, and there are molecules similar kind of in the bilayer membrane in the chloroplast. These kind of molecules are there. We call them NGDG. And this molecule, they are interacting each other. They make very beautiful assembled structure. They can hold each other. If this is polymeric system, it is high molecular weight polymer, seaweed containing molecule. And this is the molecule which is in the bilayer membrane in the chloroplast. If we can utilize those kind of surfactants for herding application, we could be able to have a naturally occurring surfactant for herding. That is exactly what I want to show you. And here we are using small pan scale experiments again in the laboratory. This is a pan, the oil will be in the middle, and this water is there. I will show you here. This is a simple example. Here we are applying different way. It is easy for us, that's why. Now we have a ring here. Inside it is crude oil. Now we are applying this surfactant, the herding agents here, what it is developed from or identified from the surface microlayer itself. And now you can see what is happening. This is in crude oil, pure water. It is you can see the oil is going everywhere. There is no surfactant, no herding agent. Now we are using this NGDG, that symbol molecule what I showed you. And if you are playing this one, you can see, the oil is not moving because that molecule which we use can keep that oil as such. It is a kind of a reverse herding we are trying to do. And the next one, you see. And the next one, we are using a surface pressure. That means we are using small amount of herding agent here. And then the oil is, you can see here, the oil is moving. Now we do the same experiment with a different surface pressure. That means we are applying more amount of herding agents. And here we are going to use surface pressure is 41. Now we are playing this with this video. You can see it is shrinking. And this shows that this MGDG, the simplest molecule we identified from ocean surface microlayer itself, can act as a sugar-based simple molecule, which can act as a very good efficient surface collecting agent. And this is a pictorial representation. If there is an oil spill, and it can hurt these same biodegradable safe molecules. If the fire is coming, it is burning off, and we can clean. And now we are interested to work with the same kind of surfactants or hurting agents in small span in the laboratory, our own laboratories. And eventually currently we initiated the collaboration between Corel, the Coral Regions Research and Engineering Laboratory. I believe everybody, including David, and everybody collaborated with them. We are already started to collaborate to work with them. We are interested to work with them right now. This is the molecule I was showing, MGDG. This is the it's a byproduct. It's available in the ocean biota. And this is plan experiments successfully show that they can be a very good efficient hurting agents. Again, this is much more of a sustainable molecular design. We can create molecules and materials designed in such a fashion that they are biodegradable and safe. And finally, thank you for your attention. I'm happy to answer the questions.
Okay. Great.
Okay, if I can have all of my panelists, Dr. John, keep your camera on, and if all of my panelists, and stop sharing your screen, and then if the other panelists can turn their cameras on, I'm going to see if this will, if all the cameras will appear at once. I've been having some issues getting, having Zoom allow me to have remote speakers turn their cameras on.
David and James come, yes. Bring a chair up and you can sit up here at the front.
So Dr. John, stop sharing your screen.
While our question and answer panel is getting set up, I'm going to announce the winners of our Being Green sign up sheet, AKA let's not get Emily's pay docked. So Angelina Kinzel and John Webster. Okay, John's still in the room. Because I like to upcycle, you get the swag put into a baby bag, baby shower bag. All right, and Angelina. All right.
Now it is okay.
All right, this is.
I don't know if I can move this.
Oh, dang it.
There's one, Tara.
Okay, I'm having to do some. Okay, we've got almost everybody. One more. Dr. John, I'm gonna let you turn your camera back on, and then I think we'll have everybody.
Yes.
Oh, perfect. Okay, so Emily, we have everybody on screen. And we are ready to go.
Questions for our speakers. And they said this is the first time we've ever had one.
That's teamwork. Okay, I don't know if people on the phone are going to hear me, but yeah, I don't know if you can. It's going to be a little bit of a question. Okay, I don't think this is the case, but I'm going to ask just to be sure. But when you're doing the test in the pan, and the oil appears to contract with the surface collecting agent, is that a result of the surface collecting agent somehow causing the oil to contract underneath itself, or is it because it's got borders to the pan that it's spreading out, and then the oil is being pushed in, squeezed in against the pan? So I'm wondering how that, if you didn't have the borders of the pan, you had a much larger body of water, and you put the surfactant around it, because the surfactant has more area that it can spread into away from the oil still push the surfactant away and not cause it to shrink?
Yeah, so the question is, does because some of the experiments that were done inside of a pan, and there's borders on that pan, would that have an effect in an open ocean? Would it have the same effect, or would the herders act differently in an open ocean environment versus in a pan environment, I guess you could say?
The answer to that, quite simply, is no. The herders do not need the walls of the pan in order to work. The mechanism for the herders themselves to spread out, they form a very, very thin monomolecular layer. The walls are somewhat irrelevant. And when I first started getting into research on it, it was kind of hard for me to wrap my head around A, how effective they were at actually doing what they were doing, and B, from a non-scientific, but a gee whiz, this is really cool, to show it and demonstrate it to other people as well. Because intuitively, everyone's used to seeing oil hit water and spread out, but to have that happen and then apply a tiny, tiny bit of herder and have the oil contract is pretty amazing stuff.
I'm curious if the kind of cleanliness of the water, the sediment of the water, affects how effective the herders are. And either are the herders inhibited or blocked at all, say there was like a large algae in the water.
It really comes down to the question was, does sediment loading or algae loading in the water affect the herder operation, performance of herders? Herders operate by changing the surface tension of the liquid at that surface interface. So it really depends on the sediment should have zero impact. Algae, because it's more of an organic compound, may start getting into it, but I don't think it would affect the surface tension of the water to a degree where it's going to show a demonstrable difference with the use of herders.
How does a surface collecting agent differ from a dispersant?
I would say that a dispersant when it interacts with the oil, it breaks the oil into smaller molecules and drops it into the water column, whereas a surface collecting agent produces a monomolecular layer around the oil and pushes it, and it doesn't interact so much with the oil internally, but on the edges of the oil.
Don't they both utilize surfactants to activate the chemical bond?
Do they both use surfactants to activate the chemical bond?
Yes, but I guess the
different type of surfactants.
Right. It really is a different mechanism, and the way dispersants work is they require a lot of energy to actually start breaking the oil into the smaller droplets as well. You need that energy. Herders in their action don't need the energy in order to do their work. In fact, if you start getting too high of a sea state, a general rule of thumb has been too much action in an ocean will start to disrupt the layer of the herder and its operation, because the layer of the herder is so thin. You're going to kind of tear it apart if the water is too rough, versus a dispersant use where you want that energy in order to start breaking the oil up into smaller droplets, and the dispersant will help keep the, well, two things. One is make the keep the droplets separate and break the oil into smaller droplets than it might otherwise be broken into.
Tim, you need to unmute yourself. You're muted.
I was going to say, I'm surprised Tim hasn't jumped in here at some point.
Yeah, let me just add a couple of things. I'd say fundamentally the dispersants are made up of surfactants and the herders are made up of surfactants. They're formulated for different things, right, as David and James were saying. But you could spray a core exit 9500 around the perimeter of an oil slick and keep it off of the oil slick, and it would do the herding as well. It might not be as effective, but it might be, right? It might depend on the oil. But the fundamental difference is you spray herders onto the water surface, right? They are surfactants, and the molecule in the herders we used are surface active molecules, just like we use in herders. They're different molecules because their goal is to reduce the surface tension of the water on the perimeter of the slick. If you were going to disperse the oil slick, you'd spray the dispersant onto the oil slick itself. But what the dispersant is trying to do is reduce the interfacial and surface tension of the oil slick itself, and the herder is trying to reduce just the surface tension of the water. So fundamentally, they're trying to do the same thing, but they are different formulations because the different formulations are more effective for one job versus the other job.
Thinking about the delivery system, the situ option, for example, if you're using that, is there a contingency for failures on that? Like if like you said, you may want to use that instead of an aircraft in some cases because it might even be quicker. But would you always have a contingency in case something happens with that technology that doesn't get to the site?
The question is there redundancy built into the system if if you have the jet ski system versus aerial system versus a vessel system? I would say, and if the jet ski didn't work, you still have two backups, or at least one backup. You can do it from a vessel. So it might be a little bit slower because he's talking 50 to 60 miles an hour, where we're talking 20 to 25 miles an hour. So, you're looking at twice the amount of time to get there to do it. And it all depends on the type of spill and what the spill is actually made of, what type of oil it is. Is it going to emulsify quickly? That may have a factor in, or if it's been sitting out there for a day, it may not be an option.
Yeah, just to add to that, I'm not sure what kind of redundancy you're talking about. If you're talking about redundancy because the jet ski, went off to Timbuktu and didn't go where it was supposed to, but used two jet skis, right? If there's a mechanical failure with jet ski, I mean, the vision we have is a big vessel would have at least two of these jet skis on it, right? So you send them both out if one fails. The redundancy, if the herders don't do what you want them to do, would be you're left with the other response options of mechanical recovery or use of dispersants.
Yeah, just the way these things are considered is they are tools in the toolbox, and if one doesn't work or has a problem or fails for whatever reason, you go back to the toolbox and see what else you've got and what's most applicable for the environmental conditions you're dealing with.
Yeah, that part wasn't part of the question, but yeah, that's important.
So there are a number of online questions, and for whatever reason they're not coming up on this version of the chat. So I'll try to. Yeah.
So did you already ask this question, right? Would the herders diminish the skimmer efficiency of the fluid-like surface of the disc?
So for our online speakers, I wasn't sure if you guys could hear that. Can you guys see the Q&A button on your Zoom screens right there, so you can see some of the online questions? But the question is whether or not the herders are going to reduce the efficiency of the disc skimmers, right? That's essentially the question.
In the research that I quickly discussed, preliminary testings that we were involved in showed that the performance was not measurably adversely affected. There was some variability in the numbers, but it's within the experimental norm. You're not going to have exact numbers from one run to the next. So,
yeah, let me just add the goal is not to spray the herders onto the oil slick, right? So the goal of herders for mechanical recovery would be to make the oil, 3 to 5 times thicker, right? So it should improve the ability of the disc skimmers, right? If you sprayed the herder onto the oil slick, just like you might change the ability of an oleophilic surface to contact the oil slick, but if you did that, you'd defeat the purpose of the herder in the first place. So
that's a good caveat. If herders are being applied, you would want to avoid spraying it directly onto the oil because you could impede the operation of oleophilic surfaces.
Tim, could you please repeat the name of SLIC, SWA, or maybe this person meant SCA you mentioned?
Oh, the name of the actual SCA that they used was Fix Slick 6535. It's on the it's in the National Contingency Plan product schedule.
I know you got a shout out because they're not going to be online if you're reading these ones.
Okay, so Tim, is the UAS retrievable back to the jet ski, or is it sacrificial?
Yeah, so the UAS is a small little drone, right? Kind of a hobby-sized drone that can carry a camera. The idea here is that it is tethered to the jet ski, so it is powered not by its own battery. It's powered, right? These small little drones can only fly for about 20 minutes, and then you have to replace the battery. So we are using an electric cable or a tether to connect the drone to the jet ski. So it is running off the power supply from the jet ski. So it can be flying for as long as the jet ski has fuel, right? 12 hours of operation. The jet ski is built with a little hanger in it, so the drone comes down and goes into a hanger so it can be retracted or it can be deployed on the tether. The idea there is you can't go 65 miles an hour with the drone flying, right? And then it needs to be protected when you're going at that speeds, and it needs to be protected if we were to ever drop it out of an airplane, right? It would hit the water kind of hard, and drones are fragile. So yes, it is retractable back into the drone. It'll go back into its hangar. But when it is being used for aerial surveillance, it can operate for as long as we maintain fuel in the jet ski. And then it also, we're doing, this is in the development phase right now, but we're looking at tethers that can go up 300 to 500 feet, right? So it can get you as high as a drone could go in the first place, based on safety concerns as well. Whether or not it needs to go that high is a question.
All right. What is the height of the tether?
You just answered that.
We just answered, I'm sorry. Okay, I think that's it then for the questions online.
Nope, there's a couple other ones. They're just not showing up there. There was a question about the inshore applicability of using herders. For instance, if there was a spill near a marsh edge, could the herders be used along with some kind of water application to effectively pull the oil away from the marsh edge and move it further offshore so that other operations can take place?
So you would, so the question is, would you put herder along the marsh to keep the oil from getting into the marsh?
Well, and then it said, I think, followed up with, I don't know if you can see the text right there. Tim, I think this is one that you answered online.
Yeah, I saw it online. Yeah, so I think the question is, you got kind of a marshy area with marsh grass in it, and oil has kind of gone up against the shoreline. And how would you get it out of the shoreline into open water so you could do some kind of absorption or skimming? And so what you do is all you simply need to do is walk along the shoreline with the herder, just like Ian Hewis did in the tests that I showed the video of and that David showed the video of, right? So you would be able to move. If you put the herder on one edge, like the shoreline edge of an oil slick or sheen that has gone up into some marsh grass on a shoreline, you take the herder and you just walk the shoreline and put a small amount under the water, and it would push, assuming the marsh grass wasn't, you know, meters and meters deep, it would push the oil slick out and potentially into open water, where you might be able to do something else to recover the oil. The question is whether or not, you know, a water deluge is encumbered by needing a pump and hose and that kind of thing. So whether or not you'd even need a water deluge is a question, but certainly if you got the oil away from the edge, you could use a water deluge to keep pushing it farther out.
I'll add here, the other aspect of this is it depends on how the oil got into the marsh area. If it's a wind-driven event, even though the herder may cause the oil to contract away from the shoreline, if the wind continues to blow towards the shoreline, that oil will in short order turn around and come back towards the shoreline, albeit as a thicker slick. So it depends on the environmental conditions as to whether or not you'd even want to try that.
Yeah, the herder doesn't have a lot of force, right? So a small amount of wind going the wrong way will have a significant impact on the herder's ability to move things.
Yeah, the bulk slick will still move from wind.
All right, okay, one more question in the room, and then we're gonna cut the Q&A short. Or not short, we're actually over. We can continue the formal discussion.
In your future testing, could you consider adding objects into the area where the oil is being herded? Maybe objects with even texture to simulate like a swamp setting, trees. See how it behaves when it's interacting with other objects.
Well, absolutely, and that kind of is a continuation of work that has been ongoing over the last couple of years, where that sort of those sorts of obstructions have been included in some tests. They just haven't necessarily been showed in the presentation here.
If you have videos of that, that would be great to see.
I do have, but not here.
All right, with that, I'd like to thank you all and thank our guest speakers, both in person and online, for joining us, and also our online attendees and in person. Thank you very much for taking the time for this conversation. I passed around some evaluations, so if you had a chance, please fill them out. That's how we fill these seminars, and also how we figure out things that you can do differently or better. So please feel free to leave them on that table or on the channel, and I can collect them later. Just one more round of applause for our guests.
If I get into this country, it's whether or not I'll be able to get out. That's the question. It is.
Thanks to our online presenters. You all may leave the meeting at any point. You can turn off your cameras and say goodbye. We appreciate you joining us. For everyone who's still online, I am going to be, I have been putting in the chat a link to an evaluation, and I am going to put that in one last time. So if you want to take our online evaluation, you can, and then I will close out this link by 3:30. Thank you so much. Our three panelists who are still online can leave at any time.